Welcome to E123 Lecture 20, 2D Signals. Woo! Great. We need some sort of refreshments, I have to say. I'm quite tired after yesterday. And I even didn't take the exam. Did you get one? You get one? Everybody has the... So we have a handout today for those who are monitoring. There's a handout which holds the password for this homework solution. I didn't tell you about that. Anybody else? Yeah. Okay. So I was thinking about it. We could have gone directly to filter design, but decided that we're going to switch and we're going to talk about 2D signals because I think it's going to be relevant to the homework you're going to get today. And I kind of like this. I looked at the whole picture, and I like where I think fitting 2D right now would be a good place. It used to be after wavelets and then sampling. We moved it to the end of the class, but now I think this is the place for it today. Okay. So today we're going to talk about 2D signals. But Julia have asked me to ask you. So help us, help you. Help me, help you. Help me, help you. You seen that movie? Yeah? Okay. Jerry Maguire. It's an old-timer thing. Anyway. Tom Cruise. Sport agent. Renee Zellweger. Anyway. It's entertaining. But help me, help you. Okay, so please, midterm survey. Please fill it up so we can help you. Otherwise, we're not going to help you. We're just going to decide. And then that's it. Okay? All right. Any questions? There's a handout. Okay, so today we're going to talk about 2D signals. 2D is my favorite topic after 3D and 4D and 5D. So the more you increase the dimensionality, I get more and more enthusiastic about it. So we're getting there. Okay. So a world is far more complex than 2 dimensions. Who took 20 when I gave these lectures at 20? So you'll see some repeated slides, but there's not a lot of them. But in 20, it was kind of like really to allure you to 123. So thanks for actually being allured. Okay, so our world is really more complex than one-dimensional. So if you think about images, there are 2-dimensional living beings. There's 3-dimensional. We live in a 3-dimensional space, right? In fact, we live in a more than 3-dimensional space. There's another dimension called time. That's another dimension. So if you think about videos, are 2-dimensional beings that change over time. So 2 images change over time. You can think about dynamic 3D scenes, one of which, for example, I even showed you. If you looked at the heart, the heart MRI images that I showed you, these are 3-dimension that changes over time. Okay, you can think of 3D videos as well that are happening today. So medical imaging would be more dimensional space. Computer graphics, they try to model light fields, and I think about 6-dimensional space there. You know, how much light is reflected from any position, what's the roughness of each position. So you can add more and more parameters and describe things in a higher dimensional space. And the question how to do signal processing and what type of analysis you could do in this dimensional space, we're going to talk about some of them. Okay, not all of them. Some of them are easily translated from 1 dimension to 2 dimensions. But of course, the fact that you have a second dimension means that there's going to be changes in those dimensions too. So, how would that going to be? How is that going to be analyzed and how to deal with it, and so on and so forth, and what comes out of it. We'll focus on 2 dimensions, and we're going to spend about 2 lectures on this topic. Just to give you a hint, it's not an image processing class, but I just want to give you some, flavor of what this beautiful things called images, videos do, and what we can do to them too. One of the things that we did see, there was remember the talk that we went in Sutar Jedi, right? That was three-dimensional signals where you had videos, and you want to emphasize their motion, very, very small motion. And there's interesting things that happened there, which I thought was, this is why I thought it would be appropriate for the class, is that there was a decomposition of kind of a wavelets, hierarchical decomposition in the spatial dimension, and then there was some filtering in the temporal dimension for different spatial frequencies. So when you heard this, you was like, what? Spatial frequencies? What even are you talking about? There's no such thing. And so today we're going to talk about what are spatial frequencies. Then that will put, I hope, this talk into more context. Okay. But I couldn't really postpone him for talking right now because he was visiting and it was a special seminar, so we gave that to you earlier. Really chatty today. What's going on? It's all this radio from last night. Made me chatty. Okay, so here's an example in the continuous time two-dimensional space. We can also think about functions. Functions are now not a function of one variable. They're a function of two or more variables in multidimensional space, in two-dimensional space. So, for example, a delta xy will be an impulse function positioned at x equals 0 and y equals 0. And if you integrate and cross the entire space, then you will get 1. Okay? If you now have a two-dimensional integral over the entire space, you evaluate the delta function, you get 1. It's infinite at 0, and it's 0 anywhere else. Okay? But its area is 1. So the usual delta function that you've seen in 120, now it can appear in two-dimensional space. That makes it a little bit more complicated because you can think of a delta impulse line, it's like an impulse line now. Right? So not just a point or an impulse function in two-dimensional space, but you can think of an impulse line. So now you can think of something that does go to infinity. If you integrate along one dimension, it has an area 1. If you integrate along that dimension, it actually is an infinite. But it's an impulse line. Okay, so that's another thing that maybe doesn't exist anymore in one-dimensional space. Here's another one. You remember the rect function in 1D? You can also have a rect function in 2D. Okay, so a rect function in 2D would have two variables, x and y, and it would be 1 when x and y are less than half in the absolute value. Okay, and it has an overall area of 1. Okay, we can also think about frequencies, or what's called spatial harmonics. In that case, you have some cosine 2 pi with a frequency. So if just remove this, you've got a frequency in x, right? This is just a usual 1D frequency. But then you can add another frequency in y. What does that mean? And these are, in fact, spatial harmonics. And once you have spatial harmonics, you can also, of course, think about spatial frequencies and decomposition to those spatial frequencies and what do these mean, and so on and so forth. You can also think about circularly symmetric type of signals. Now they're not, there's no such thing really in 1D. For example, you can write this function as a function of r. So this is a rect function, but it's not a function of x or y now. It's a function of r, of a radius. And that would look like this. Okay, so it'd have it's kind of a pillbox. Okay, so now it's actually a function of one variable, which is the radius, and so it's for every theta. You can think about the other coordinates, right? Like r and theta, not just x and y. It will be a pillbox, and the question is how's that look in the frequency domain, for example? So yeah, spatial frequency. So what is really a spatial frequency? Spatial frequencies we can think of, again, as just either complex harmonics or cosines that change. Instead of changing over time, they change over another variable, for example, space. It could also vary space and time, right? It could vary, one-dimensional space and one-dimensional time. But they vary in a sinusoidal kind of way, either through a complex exponential or a cosine or a sine with different phases. Either it's real or complex and so on and so forth. Okay? So if you look at the page that I gave you, right, and you look, for example, this column over here, you kind of see something that changes periodically in space, right? So it has a spatial frequency. And the units, if we use space as centimeters, then the units for the frequency would be 1 over centimeters. Or if we use the angular frequency, thank you. The angular frequency, it will be radians per centimeters. Okay? So its inverse centimeters will be the frequencies. Much like hertz is really inverse second. Okay? So the unit of frequency is always inverse the measure of either distance or time and so on and so forth. Now you can also think, if you want to kind of imagine what is a spatial frequency, you can think of kind of the vinyl record. Now they're coming back, right? It used to be really hard to teach this, a couple of years ago, but now, you go to Target, you see, things that you can read vinyl records on. And a vinyl record, for those who haven't been updated yet with this new trend that's coming up, you have often a diamond needle that goes into a grooves embedded in plastic on this device called a record, okay, a vinyl record. And then as the record rotates, the grooves makes it vibrate to the sides. Could also be up and down, but it's mostly to the sides. And though this basically creates, there's of course some change from mechanical vibrations into electrical that are then played as sound. Okay, so it goes. This idea goes a long way back to Thomas Edison, who actually first to implement this kind of an approach. Okay, so you have these grooves; they're beautiful. But if you think about this, now what you're mapping a one-dimensional time signal you're embedding it in a two-dimensional space. So it's still a one-dimensional signal, but it's now embedded in a higher dimensional space. You thought about that? Right? So you could potentially kind of unroll it, right? And just think of it as just vibrations over time. Okay? So that transforms temporal signal into a spatial signal, right? So whatever was played here, whether the Beatles or so on and so forth, that is translated into a spatial variation, okay, that you see here. And this is a SEM version, image of this. Beautiful. Okay, so you can also think of not necessarily analog frequencies. You can also think about digital signals. So this is a photograph of a CD-ROM. You know what a CD-ROM is? It's like a Blu-ray, but not as dense. Okay. And so a CD-ROM will have basically the bits, zeros and ones, and then a laser would read those bits. Either it's reflecting or not reflecting. Okay. Kind of an on-off keying type of modulation. Okay, so now we can ask what's the spatial frequency, and we can do this like a millionaire show kind of thing here. All right. So let's say we have the following signal: sine 2 pi fxx plus fx fyy. These are the spatial frequencies. This is the variable, and the question is, what is the spatial frequency? Any volunteer? You want to go for it?
Is it B?
Are you sure?
Can I make a phone call?
How about 50-50? So the answer, yes, that's right, is B. And why this is B, right? Why this is B. So what you do is you count the cycles, and you look at how many centimeters, and you want to see how many cycles per centimeters you get. Okay. So let's see the variation in X. Which is this is Y. So what's the variation in Y? No variation in Y. Here, no variation in Y. No variation in Y. Okay. So 0 per 2 centimeters means 0. Okay. So that's good. And how many cycles here? 1 cycle, 2 cycles. 2 cycles per 2 centimeters means Fx equals 1 inverse centimeter. Okay. Well done. Who's the next one? Who wants to go? Come on, wake up. Okay. C. Are you sure? You want 50-50? I have it programmed anyway.
Yeah, C because it's offset.
C is yeah, so this is a sine or a cosine? Right? How do you know?
Because it starts halfway through the y bar.
It's in the middle, it's actually positive, right? Cosine is positive at 0, right? So I didn't actually tell you what is the color map here, but you assumed that it is, and that's very nice of you. Thank you. Yeah, you're absolutely correct. This is cosine, and again, you can count the spatial frequencies. There's no change in X. There is changes in Y. There's 1, 2, 3, 4 cycles per 2 centimeters means that Fy equal 2. It's a cosine because at 0 it is 1, right? It would a minus cosine if white was minus 1, okay? And if it was offset by, if it was gray, then it would have been a sine. Okay. All right, anybody else wants to go to the next one? Who wants to go? I should have asked before I put it up. Yeah. Are you sure? Actually, I think I have a mistake in this slide. So. Well, let's just count them. Which one did you say? A? You might be correct. I think this is a slide that I always have a mistake. But I forget to fix. All right, let's count. So let's from here. 1 cycle, 2 cycles. 2 cycles in 2 centimeters. So Fx equals 1. Yes, it's definitely the mistaken one. And how many cycles here is 1, 2, 3, 4 cycles for 2 centimeters. Yes, it is A, and A is the answer, and I should write that. This is the answer. For next time. Okay, excellent. Ready for the next one? Who wants to volunteer first? You don't know what it's going to be. Yeah, who wants to volunteer? Ready? Okay. Oh, that's the fixed one. Actually, no. Okay, that's the one. Okay, ready? Final rotates at 1 hertz. What is the temporal signal? The time signal that comes out of it. Ready? And? Just to confuse. This is like a vinyl record, right? I can't hear you. There's music. A. Are you sure? I mean, the velocity changes as you go closer, right? The velocity changes. Does the frequency change? No, because it's the angular velocity is the same. Right? Okay, so what you do then is count how many cycles per cycle, per circle. So it's 1, 2, 3, 4, 5, 6, 7, 8. 8 cycles. And it rotates at 1 hertz, so 8 hertz. That's right. Very good. And who wants to do this one? Next one. Come on. It's going to be fun. No, you did it already. I'm going to pick one. All right. Ready? Why? No, this is how I render it. The spatial frequency is too high for to represent it. So we're not able to sample it enough fast. The spatial frequency is changing, but the actually angular frequency is not going to change, right? But when we try to render it, as we get closer and closer to the center, in order to represent the same angular frequency, you need much higher spatial frequency. Okay? And that's why we got aliasing, because I didn't, well, first of all, if I low-pass filtered and then sampled, then we would just get like kind of a smooth thing, right? But that's not what happened. What happened was that I get aliasing because I didn't low-pass filter when I rendered it. I just put values. And so as you get closer and closer, there's just not enough representation in this particular image to represent this fast frequency, which is kind of cool. But also it leads to the, you know why there's a label on a record? There's a label on the record.
Oh, because it was center.
There's really no point of doing in the center anything, because we're not going to have the resolution, the spatial resolution, to actually make these grooves so fine to provide you with enough temporal resolution. So this is one of the reasons. Okay? So it's actually, if you think about the frequency, basically the accuracy, like if you want to represent a high frequency in the middle, or the high temporal frequency in the middle of the record, and a high frequency at the edge of the record, it will have different spatial frequencies. Okay? This one's will be more stretched. You're going to have a homework problem about that, about scanning something with an optics. If you go faster, what happens? If you go slower, what happens? If you use anti-aliasing filter, if you don't use anti-aliasing filter, what happens? Okay, so count the grooves and so on and so forth. And which one? A, that's right. Well, I guess it's none, because when you get to the center, it changes frequency. Yeah. So it could have been A, but no, you got aliasing, so it's none. Okay, so then this is what you got, actually. And this is the challenge that basically I recorded a password in audio, and I embedded this as intensity is in the image. Each column represent basically, so I mapped this one-dimensional space into these blocks. So this is the time equals 0 to 1.25 millisecond. This is 125 milliseconds to 250 milliseconds, and up to 2,000 milliseconds. So basically, if you draw a line in the middle of each one of these columns, and you concatenate them and play them in Python, you'll hear my voice. So what you need to do is you need to go home and either scan it on a scanner, or take your phone and take a picture of this thing, and then in Python, basically, crop the right samples and then play them, and you'll figure out what the password is. Okay. And if you do it well, and if you actually do it, you need to make sure that the scaling is correct. You know, that the whole signal should be played at 2 seconds. You know, if it's more than 2 seconds, means that my voice is going to sound pretty weird. And so you have to filter it accordingly and decimate and so on and so forth for it to be 2 seconds. And then you'll hear the password. Yes, this is a 21st century vinyl record that you optically read it. Yep.
Are the intensities normalized?
All right, that's fun. You're going to hear something. To the homework, to get the homework solutions. If you don't have the password, you don't get the homework solution. I just decided it right now, so we're going to figure that out later and see how we can implement that. The what?
You must enter the password. You know, just the homework.
That's right, yeah. Any questions? So this should be fun. It shouldn't take you long, but you have to figure that out. That will help you also do the homework too, because you understand kind of the scanning thing and the speed and so on and so forth. Actually, the reason that I thought about this, there's a project at LBL that what they did is they scanned old records, and like even one of those really old ones that were engraved in wax, because you don't want to really touch them anymore because they're going to break. And so they just scanned them optically, and then they basically inferred what if you had the device, how it would play, all in signal processing. Okay, so it's kind of cool. All right. So once you actually define a two-dimensional signal, we can also define a two-dimensional Fourier transform. Okay, we have spatial frequencies, right? So if we have spatial frequencies that change in space, then we can define a two-dimensional Fourier transform. And how it's defined? Well, it's the integral from minus infinity to infinity of the two-dimensional function e to minus j2 pi, and then again spatial frequencies, and you integrate over x and y. Okay? The reason I'm showing this to you is because if this is a brain image, this would be the magnitude of the Fourier transform, the two-dimensional Fourier transform of that image. Okay, there is also a phase component that I'm not showing you, but this will be the magnitude of this two-dimensional Fourier transform. And the reason that I'm showing you is because this is actually where the data is acquired in MRI. In order to reconstruct, you really need to take an inverse Fourier transform to get this. Okay? So in MRI, you're actually acquiring data one line by line, and as you get more and more data, you're able eventually to reconstruct kind of the object. And so if you only capture, let's stop here. Stop. Why can't you just stop? Oh, no, you stop me? Let me see. Okay. Obviously, the spirit of Steve is just preventing me from doing this. But the point is that you first, if you look, you only see the edges. Edges are high frequency. You see edges. Then you go through the low frequency, and then you start seeing something. Okay. All right. So once we describe this, we can look at two-dimensional, signals and look at the two-dimensional Fourier transform. So this is a two-dimensional frequency. So the two-dimensional Fourier transform, I can describe it either as the intensity of an image, but also as a surface. Right? That's another way to describe it. Taking a Fourier transform, what's the Fourier transform of a sinusoid? Two impulse functions, yes, and we have two impulse functions. But those impulse functions depend on the direction now. Right? And this is a low frequency, so they'll be close to each other. What happens if we go to high frequency? They'll separate. So whatever is high changes fast in one domain is reversed in the other domain. Okay? So high frequency, this is what happens to them. So they're further away. And they're a little bit offset because there is some y spatial frequency. and there is also an x spatial frequency. They're both. That's why they're a little bit tilted. You see another really cool thing? This is a two-dimensional sinc. It is a two-dimensional sinc function, and the Fourier transform of a two-dimensional sinc function is a two-dimensional rect. But the rect doesn't have to be. So if the sinc function is not the same scale in one dimension, that means that the rect is going to be scaled differently in the other domain. So you see whatever changes really fast. This dimension changes fast, then it's more stretched. This dimension changes slower, then it's less stretched. Okay, so this is how you can get, for example, this rect. Now we can, of course, change it and, squeeze it even more, like stretch it even more in one domain. So now, it doesn't change as fast at all, and so it's going to be really squeezed in the other domain. Okay? Remember wavelets, right? Whatever is stretched in one domain represent, something that is more compact in the other. Okay? So this would be a two-dimensional filter if you convolve with that. Yes?
Why isn't the base of the rect on the right like a 90-degree angle?
Oh, this? Oh, this is just a rendering. No, it is. Well, because I cropped it, first of all. So it's cropped when I compute the Fourier transform, so it is a little bit windowed. So, that's great. But remember that we're going to deal with discrete signals, right? It's not a continuum. So we'd like to also define the 2D DTFT. Okay, the 2D DTFT would be sums over n, where n goes from minus nx and ny, the indices of n, going from minus infinity to infinity. And this will be continuous, omega sub x and omega sub y, that are going to be defined from minus pi to pi, and then going to be periodic with 2 pi. Okay, but periodic, each one in its own domain, so it's kind of like, block kind of period, periodic in a way that it repeats not only here, but it will repeat also here, and it will repeat also here. And for those listening, I'm just doing something with my hands. So there's other ways that you can describe it. So this is the way we're using angular frequencies, but you can also use digital frequencies. Digital frequencies goes from minus half to half, and you just multiply by 2 pi over here. Okay, I prefer actually the second one. This is what we use in MR, and I like it. The reason I also like it is because there's the inverse and forward that doesn't have the 2 pi, whereas this one, the going with the inverse, has a kind of a 2 pi that you have to divide by. With this representation, you don't. So the cool thing about this is that if you actually massage this algebraically, you can actually show that the way to compute this, and one way to compute this is first compute the DTFT in one dimension, and then compute the DTFT in the other dimension of the result. So you can actually separate that. Okay, they're separable transformations. So you only need to know how to compute a 1D DTFT or DFT in order to compute the two-dimensional one. You first compute it in one dimension, then you compute it in the other dimension. Okay, and it's very easy to show. So if we're talking about then the DFT, this is exactly the same thing. Now we not only discretize the indices in the image, we also discretize the spatial frequencies. Okay, so the spatial frequencies are discretized to quantas that are vary with basically n. Yes, nx times kx over n. Okay, so these are the quantizations. So it's kind of sampling the two-dimensional DTFT in the very similar way that we did for the 1D case. Okay. Now, in order to compute a two-dimensional Fourier transform, the cool thing, because it's separable, you only need to have a 1D FFT. You run all the columns or the rows, and then after you do that, you take the result and you run on the other one. Okay, if you started with the columns, then The second run, you run over the rows. So the complexity is still n log n. Okay? It's still n log n. Or depending what n is, if n is one side, then it's n squared log n. If it's, right. Any questions? Yeah, I didn't really teach you anything that is substantial so far. Just basically, this is all easily translatable from 1D to 2D. Okay, so the 2D DFT. One thing that you have to remember that in the case of much like in the one-dimensional space, where nx and ny are mapped such that 0, 0 is in one corner of the image, right? And so are the spatial frequency are at the corner of the image. If you want to relate that to the DTFT, in which 0 frequency is in the center of the image, you have to do an FFT shift. Okay, you have to do an FFT shift for it to show. Now, often we'd like to do when we look at an image, what is 0, 0? Like often we'd also like that to be in the middle. So one thing that you need to do actually to compute the right thing, you have to do FFT shift before you compute the FFT, then compute FFT, and then FFT shift again. Okay? The first FFT shift moves this to the middle, and then you do FFT, and then FFT shift again. Okay? And that actually gives you the right thing. So you have to do FFT shift twice. The one thing I have to mention that if you have a time signal, and you're considering t equals 0 also in the middle of the signal, you also have to do FFT shift twice. Okay? But often when we look at time, we don't think of negative time, so we put time to be the first index. Time equals 0, the first index. That's often why. Okay? But in images, it doesn't make sense to like the corner to be 0 for some reason. We always like it to be in the middle for some reason. Especially in MRI, where the middle is kind of the center of the magnet. Okay? So it makes more sense to put 0, 0 over there. Okay, so some properties of 2D DFT. Of course, you can define a convolution, a two-dimensional convolution, a two-dimensional, actually circular convolution. The result in the frequency domain will be again, a multiplication. Okay, two-dimensional circular convolution will be multiplication. Circular shift would correspond to a linear phase, so a modulation. So a modulation multiplied your signal in a very similar way to the one-dimensional case. Let me show you an example. This is an MRI scan of a phantom. Phantom, we call anything that's not alive that we put to test. Okay, so this is a cross section through this acrylic plastic enclosure that has shapes in it and also water. So shapes in plastic and then water. So it's kind of this big cylinder. Okay, and we look at a cross section through it. Whatever is white means that there's water filled in. Whatever is black means that there's plastic there. So you just don't get a signal out of it. You only get the signal from water. Okay. So this on GE scanners, they use this phantom to test the scanner and make sure that everything is right, that the geometry is correct, that you get good image quality, and so on and so forth. So this is they sell that for every scanner, and every scanner you just run this testing on it, and you can calibrate the scanner based on it. Okay, because you know exactly what it should be looking like. Okay. So this is the image, and this is the two-dimensional Fourier transform of it. The magnitude two-dimensional Fourier transform. Remember, I'm not showing you the phase. Okay, but there is a phase here, and I want you to kind of point out maybe something that's kind of strange here. Can you see something that's weird?
4 dots.
Yeah, 4 dots here, right? 4 dots. 4 dots. Where are these coming from? Which one?
That probably come. I think the 4 dots.
The 4 dots are coming from the cone that has 2, 4, 5 dots. You can still say yes.
Yes.
I just said that to confuse you. Now, why would you see dots like that, though?
Because of the high frequency changes between.
There is some frequency there, right?
Yeah.
It's kind of like an impulse train that is diagonal. What's the Fourier transform in an impulse train? But what's the spacing between the impulses? It's like inversely, right? So if you have something that's really close, then you have these things spread away, right? That kind of makes sense. Now, why they're not like impulses? Exactly. Because it's truncated. So the whole truncation, the fact that it's finite, right? It's kind of like a multiplication with a rect, which is a convolution with a sink, right? So that spreads them a little bit, okay? And you also notice that this one is a little bit weaker than this one. That's because each one of these elements have some width, right? It's not that they're just the whole thing is truncated. So there's this truncation here. This is truncated, so you just get the distance from here to here. It doesn't continue, right? So that truncation blurs this. But each one of them also has a width. So that's a convolution with a small rect. Convolution with a small rect is, in the other domain, multiplication with a wide sink, which attenuates, attenuates the corners. Okay, so it's kind of hard to see, but yeah.
So if our cone teeth were shorter, then it would be longer.
If they were close to each other, then these will be away. Yeah.
Not closer in with this way, but closer like they're shorter.
Oh, if they're shorter, then you'll have wider in this direction. Yeah. They'll be wider in the diagonal if they were narrower. Yeah, for sure. Yep, in the same direction. They'll be basically blurred. The other thing that so how do you know, by the way, that it's coming from the comb? I mean, how do we know, right? We suspect that these are these, but how do we verify? What? Yeah, get rid of them. Let's get rid of them. Oh. Cool, huh? You want to see? Yeah. Oh. Cool, huh? Almost not touching nothing else. Actually, it does touch some edge frequency too, right? So it's mixed, but the majority of the signal there comes from this. What else we can see? There's this line over here, right? And this line over here, where they're coming from? All the edges perpendicular to those directions. So the line. This line is coming because of edges here. Edge spreads out, right? You can see, but they're kind of constant, very, very long, right? So they'll be very compact in this direction, in this dimension. So long lines over here translate to, something like this. So we can remove them too. See how it blurs it? See that this almost goes away because it's so blurred. Yeah. So other properties. If you rotate, there's no such thing as rotation in one dimension, right? What happens if I rotate the object? What happens to the frequency domain? Also rotates, right? Because it makes sense, right? It tracks the exact frequencies of the object. right? It shouldn't change. So the frequency also rotates with the rotation, right? What about shifts? What if I shift the frequency domain? We talked about this, the shift theorem, right? You've shifted the image domain, you get, right? Wow, if you circularly shift, you get complex modulation, right? If you circularly shift the frequency domain, what do you get in the image domain? Modulation too, right? So shifting creates modulation. So does the modulation change the amplitude? Does it change the magnitude? No, it just adds phase. Oh, so lucky for MRI. So lucky for MRI. The reason is, so here's, I shift a little bit circularly shifted the magnitude. I get the exact same magnitude image, but now if I look at the phase of that image, I see a linear phase. Here. Why do I get all this crap? Where do I get all this crap? Yeah. Right. For small magnitude, phase is really not defined. So small noise throws the phase away. Right? So this is why it looks random. Okay? But phase is really defined when the magnitude is high. Okay? So the phase is linear when the magnitude is high. It's not linear. It's like we don't care actually what it is when it's low. Okay? The reason I say it's good for MRI is because in MRI sometimes there's a delay between the hardware and the receiver chain. There's two different chains. So you change magnetic fields on one end and you sample at the other end, and there might be some, delay between these. These delays would translate into a shift of the frequency domain, which does not affect, for this particular case, the magnitude of the image, which we often just look at the magnitude. Okay, so that's a good thing. All right, you want some debugging? MRI debugging, artifact debugging. It's a real one. Yeah? What's beautiful about MRI is it's all about Fourier theory, and everything that you see, artifacts, like I showed you before, Gibbs ringing, remember, and aliasing that MDs have to learn about. Here's another one. This is an artifact that we got when we acquired this image. What is it coming from? What would generate this? Yeah? Anything? Yep.
So it looks like multiplication by sinusoid with space wave. So
could be a multiplication. Could be. Yeah. Could be. But that's a good thought.
It could be like convolution with deltas, which would be what aliasing looks like. So if you have two stacked on.
You need a convolution in the frequency domain, right, to get modulation. Right? It's not the physical convolutions. There's nothing that really...
Two copies of the frequency spectrum
that are shifted. Yeah. Yeah, that could have generated this, but this is actually not what happened. But it's close. Well, I like the diagnosis. It could have been, but that's not the case. All right, I don't have much time, so I'm going to give you the answer. Okay? The answer is spikes in the data. Okay? Something sparked, and there are, the A to D picked up like a high signal. That's it. Picked up this high pixel, large pixel, which then was translated to a complex exponential that was added to the image. Okay? Added. But why would a complex exponential generate that thing? And the reason is that if you have 1 plus e to the j omega with some omega 0 times omega, okay, and you look at the magnitude of that, because this is what we're looking at, the magnitude, then for omega equals 0, this is 2. For when this is actually pi, this equals to 1, minus 1, and those cancel. Okay? Right, so then you've got this modulation. But this is because this is only a one-sided spike that creates then cancellations in phase in the image. Okay? If it was a cosine, then it would be 2 spikes, and then you would just see like a sinusoid that's added. But now, because it's, anyway. So that's the reason. The magnitude of this actually oscillates from 0 to 2. Okay. Cool, huh? It appears all the time. Yeah. You know how they deal with this? They have a spike detector, and then they just remove the sample and locally average it. It's kind of like a median filter, right? If you think about this. So yeah, it kind of makes sense, right? This is what we talked earlier, right? You need some nonlinear filtering to get rid of that, because no low-pass filtering will get rid of this kind of signal. Right? It will even spread to other ones. Right? All right, have a nice weekend. See you next time. We're going to talk about tomography, which is the reconstruction of slices from projections. This is how CT works. So we're going to talk about them.